masking for efficient, selective whole word masking for efficient domain adaptation of Arabic language models. Dr. Khayati, you have 10 minutes to present. Okay. Please share your screen. Or Yasin will be presenting. Yasin. Yasin. Your voice is not clear, Yasin.
How about now?
Yeah, now it's perfect. Yeah, please share your screen.
Yes, just a second.
Please.
The button was already here now.
It's at the top right corner.
Yes, it's at the top right corner, but I couldn't find it. It was right here now.
If Dr. Zakaria has the presentation, maybe he can share and you can coordinate. I don't know. Works fine.
I will leave and try and come back and see if I can.
Okay, please. You can leave and we'll join again, please. Yeah.
Hi.
Yes, hi. Can you switch on the camera and share, please?
Yes.
No problem, Yasin?
Yes.
Can you find the share button?
Yes. Yeah. How about now?
Yes, yeah, we can see your screen.
Yes.
You have 10 minutes, Yasin, to present, okay?
Alright. Just a sec. Yeah. You can see the screen, right?
Yes, we can see the screen, yes. You have 10 minutes.
Yeah, hi everyone. Hi everyone. Today we're going to talk about selective whole word modeling for efficient domain adaptation of the Arabic language, presented by Yasin, the National High School of Artificial Intelligence ASIA, and Dr. Abdel Zakaria at the Abu Dhabi University. We're going to talk first about the problem, the insight, the method, then the experiment, the impact, and finish by the conclusion. We'll start with the problem. When it comes to Arabic, we have essentially two different words. We have the modern standard Arabic, which is the written Arabic used in education, media, and official documents, and the spoken Arabic, which are the regional dialects that differ from one region to the other. One example could be the sentence "I want to eat," أريد أن آكل. If we were to translate it to the other dialects, to the other regions, in Algerian it would be راني حاب ناكل, in Egyptian it would be عايز آكل, in Moroccan it would be بغيت ناكل, and in Gulf it would be أبي آكل. So they are all translations of the same sentence, I want to eat. One other representation would be this map, where we can see the Arab countries and their respective dialects. As you can see, many countries tend to have more than one single dialect, to which there are actually many solutions. For example, Camelbert DI, Marbert, and Camelbert Mix are all NLP models who have been fine-tuned and trained on dialectal Arabic, and they did drop the perplexity by up to 30%, but it introduced another problem, which is catastrophic forgetting. Catastrophic forgetting is essentially when the model fails to remember MSA. So if we were to take an MSA model trained on dialect and give it an MSA input in which it was trained, say in our case, a man went to the market, الرجل ذهب إلى السوق, the model, for example, would misunderstand the word went, ذهب, which means that the performance impact is that the model forgets MSA. And there is also the high cost of fault retraining, computational and data cost require millions of tokens and weeks of GPU time, and the environmental cost that it does emit 1,400 kilograms of CO2 per model, which equals to driving 3,600 miles. And it's impractical for low resource dialects where large datasets are unviable. So essentially, the brute force approach is environmentally unsustainable. And here comes the insight: when taking an MSA model that was trained on MSA to train it on dialectal APIC, random masking is simply inefficient because we might fall in the case where we're training the model on dialect-specific terms in which it was already trained. One example could be training it on the words and, wa, and fi, in, and the bad arakulu could be a case. So the solution is to use a smart masking, which is much more efficient, that focuses more on dialect-specific terms. For example, it would focus in aya, rani, or serta, or I want, brit, for example. And in the training phase, we would use the IDF, which is essentially an unsupervised statistic that quantifies the word uniqueness. The formula is simple: it's the logarithm of the number of words divided by the number of words in which it's the number of documents divided by the number of documents in which our word was present. So essentially, if our data set is mostly MSA documents with some dialectal APIC terms, so essentially the dialectal APIC terms would have a high IDF, meaning there are. So a high IDF means there are, which is likely a dialect-specific term. One example would be Algiers, Zaire, would have a high IDF of 1.39. On the other hand, the low IDF would be common and general, likely a common MSA term, such as one example is fi, in, which would have a low IDF of 0.69. And in the adaptation phase, we would use the selective whole word model masking, which would mask 50% of the token following the standard 80-10-10 ratio, but assigning the masks by probabilities using the cross-lingual IDF score to prioritize domain-relevant terms. In other words, the probability that a token would be masked is simply the IDF of that token divided by the sum of the IDF of all the other tokens, which would give us much better the probability distribution when it comes to probability distribution. For example, the sentence "the weather in Algeria is hot," the probability distribution would be way better if we were to use the uniform way. All of them will get a 25% chance of being masked. But if they were weighted by the ADF, more MSA terms would have a lower probability of being masked compared to actual dialect-specific terms. For example, الحال, في, the weather, in are more MSA terms, so they would have a lower probability. And terms such as Zaire, Algiers, and Skhon hot would have a higher probability since they are more dialect-specific terms. So, although yes, it does make the training more efficient, and faster, but keep on training it on the only MSA specific terms, training it on dialectal terms would lead us back to our main problem, which is catastrophic forgetting, to which we did present the solution, which is when fine-tuning and training the model, we'd use an edited loss function. Our loss function would have a 70% loss on the MSA, and 30% would be the loss on the dialect. And this 70-30% ratio would maintain 95% of the original MSA performance while effectively learning the dialects. And to evaluate this model, we'd use single token perplexity. So for each sentence, we mask a word at a time and ask the model to predict it using the rest of the sentence, and the average the quality of these predictions across all tokens defines the final perplexity score. So the perplexity score formula is IQ1 It would be simply the exponential of the sum of the logarithm of the probabilities of the predicted words divided by minus 1 over the total number of predicted words, which would eliminate the need for expensive labeling, for expensive labeled data. One other example would be simply using a sentence, say, I'm tired, Rani Ayan, if we were to mask the word I am, which is Rani, and give the model Ayan, and it would predict Rani. So basically, the lower the perplexity is, the better is the dialect understanding, and the less confused our model is. Here's another example. When it comes to experiments, our experimental setup, we use two datasets: the Mardar dataset, which has 4 dialect clusters, and the PADIC dataset, which has 6 regional varieties in our method. As for the models we used MSI models such as BERT and CamelBERT and others, and mixed models such as MAR-BERT and others. MAR-BERT, CamelBERT mix, and others. When compared to the Mardar 26, the perplexity does drop by 72%. Here we can see that our model's perplexity on Algerian was 62.9, on Tunisian 58.4, on the Moroccan would be 123.2, and on the MSA it would be a bit worse, 62.42, but on average the improvement is 72%. It's clear that you can see, for instance, if we were to take CamelBERT mix, it would have a perplexity on the Moroccan 626.7 compared to ours 123.2. Also, when it comes to the PADIC, our method's effectiveness isn't limited to one dataset. It generalizes across all tested dialects, including non-Maghrebi varieties such as Damascus dialect, with a 72.95 perplexity. Here are the results compared to MSA and dialectal Arabic models, as you can see. And one better way to visualize the results is when it comes to comparing our model to CamelBERT MSA and CamelBERT mix. CamelBERT MSA is in blue, CamelBERT mix is in orange, and ours is in green. As you might see, when it comes to the MSA, they essentially do have the same perplexity, or near enough same perplexity. Then when compared to the other dialects, there is a huge difference. If you can see, when it comes to the Algiers, the Annaba, the Tunis, Damascus, or the Rabat dialect, you can see now the huge difference in the perplexity. And what you can see, what the thing you can visualize is that the usual solution in which CamelBERT mix used simply.
Yasin, you have 1 minute. You have 1 minute to finish.
Yeah, it's simply ineffective because what CamelBERT mix is trying to do is to train the model enough so that it understands dialect, and enough so that it doesn't forget the MSA, instead of our solution, which changes the loss function, which would give us much better results compared on all other aspects. So when it comes to the impact, it's efficient, sustainable, and practical. 30% less GPU time, 60% less data, and 120 kilograms saved per model of CO2 saved per model. And it does generalize to beyond Arabic. It can be the core insight, or the core training and data and algorithm, training model and algorithm does generalize to move beyond Arabic. It can solve problems with Swiss German, for example, Haitian Creole, spoken Tamil, or all other low resources languages with indigenous and minority languages. As for the conclusion, a simple idea with bigger results, with big sustainable results, 72% better perplexity, 40% less GPU, is a practical route to inclusive and sustainable NLP. Thank you.
Thank you, Yasin, for this interesting presentation. Anyone has any question, please? Yasin? No questions, so Yasin, thank you so much, and good luck, inshallah.